Hi everybody, I hope you're having a wonderful day. Today we're going to talk about colligative properties, and specifically 3 of those colligative properties. So let's define what colligative properties are first. Colligative properties are properties that depend on the collection. In other words, it depends on the number of particles or your concentration rather than on the nature of the particles. So it wouldn't matter if you're putting in like sucrose or glucose. What matters is how many particles you are adding. So these are properties of the solvent that change when you add solute, and they change based on the number of particles of solute that you add to your solvent to make your solution. So let's write that down. So they are properties of the solvent that change depending on the number of solute particles that there are, not on the nature of what the solute is. So it depends on the concentration or the number of particles, not on what the solute nature is. And the first property that we're going to look at is the freezing point. Freezing point of a pure solvent will change if you add some solute particles to it. And so let's talk about the details of that. So first of all, the freezing point of a substance is the temperature at which the solid and the liquid phases are at equilibrium. So for water, for example, it is 0 degrees Celsius. And the change in the freezing point is directly proportional to the number of solute particles per mole of solvent particles, which makes it a colligative property, meaning that the change in the freezing point has to do with the number of particles, again, as opposed to the nature of the particles. So let's see what happens with the freezing point. So let's take a look at these 2 particle diagrams. I've drawn 2 boxes with some particles in them. As you know, I'm not very good at drawing, so just assume that these are all the same size here. These are all solvent particles. Let's say water, for example. So here's my solvent, just pure solvent by itself, and now I'm going to make a solution. So I'm going to add to this some solute particles. So let's make those red, for example. So I have them here in green, and so the green, again, are my solute particles. To the solvent and the solute together make a solution. So I want to compare those 2 particle diagrams. In order to freeze a substance, you're taking it from the liquid form to the solid form. And so the main difference here is the position of the particles. In the liquid form, they're kind of random, but in the solid form, they line up and make a nice crystal of rows and columns in repeating patterns. So imagine if you had this, and those need to line up so they make a nice orderly crystal with rows and columns, versus this one. Which one would be easier to freeze? This one would be easier to freeze because here your solute particles are in the way. So it is harder to freeze a solution compared to the pure substance. So because it's harder, I have to freeze it at a lower temperature. In order to freeze a liquid, usually you have to cool it down. And so comparing a solution to a pure solvent, I have to cool down the solution even more than the normal solvent by itself in order to freeze it because the solute particles are in the way. And so we say that the freezing point depresses or goes down, hence freezing point depression. Another analogy, or one analogy for this is, let's say that you guys are sitting right now and you are in the liquid form, and let's say you're standing up, standing next to each other, all in a group, all close together, standing together as a liquid. And I tell you, hey, turn into a solid. So as particles, if you're freezing or turning into a solid, what you're going to do is you're going to try to line up in rows and columns. So let's say you have to do this when the room is completely empty, versus if the room has some chairs or desks in it. If you need to line up real close to each other in a nice orderly pattern with rows and columns, like in a crystal, it is much easier for you to line up correctly if the room is empty, versus if the room has desks or tables or something like that that would get in your way, then it's going to be harder for you to line up to make that nice crystal. And so the desks and the chairs here represent are solute particles, and so they get in the way of the particles turning into a solid. And so again, it is harder for a solution to freeze compared to the pure solvent, and the freezing point goes down or depresses. Mathematically, if I wanted to write an equation for the freezing point depression, if I wanted to calculate it, how much does it go down, here's the equation for it. Delta TF is equal to KF times M times I. And let's talk about each of those variables here. So delta T, delta is the change, T is temperature, and F stands for freezing. So this is the freezing point or the freezing temperature. So the change in the freezing point, so how much it goes down by, is equal to KF. In chemistry, K stands for constant. So this is called the freezing point depression constant. And it is different for each solvent, so you look those up. If you're asked a question on a test, that number would be given to you because it's a constant and it's different for each substance. M is your molality, and then I we will talk about a little bit later. Don't worry about it for now. So I'll write those down. I'm sorry, I kind of don't have a lot of room here, but so again, delta T is the change in the freezing point, K is a constant, and then M is the molality. And if you remember, molality is moles of solute over kilograms of solvent. So let's try a problem together. It says, calculate the freezing point depression of a solution of 100 grams of ethylene glycol, which is C2H6O2, in a 0.500 kilogram sample of water or solution of water. Kf for water is given as 1.86 Celsius per mole. So we're going to start by writing out our equation. Okay, so delta Tf is equal to Kf times M times I. And we are going to solve for the delta Tf because we're looking for the change in the freezing point. Kf is given to us. It is 1.86 Celsius per mole. And then the molality, like we said, is moles per kilogram. And so you can calculate that separate and then plug it in, or you can do it all together. I'll calculate it separate and then plug it back in. So molality is moles of solute over kilograms of solvent. My solute is my ethylene glycol, so I have 100 grams. And I'll change that to moles. The molar mass is 62 grams per mole. So that's my moles, and then I'm going to divide by the kilograms of solvent. I have 0.500 kilograms. So my molality is going to be 32.1 mole. Oh, excuse me, that's 3.21, not 32.1. So 3.21 mole. So now I'm going to plug that in back in my equation. So I have my Kf, then 3.21 mole. And I told you not to worry about the I for now. The I only counts if it's ionic. If it's covalent, like ethylene glycol is covalent, and I can tell that because I have all nonmetals bonded together. So if it is covalent, you just ignore it or you put 1. If it's ionic, then you need to actually put something in, which we'll talk about in a minute. So anyway, molal on the bottom, molal on top, those cancel, and I end up with 6.00 degrees. Actually, sorry, 5.97 degrees. So what does this mean? This is telling me that my temperature, my freezing point, drops about 6 Celsius or so. And so if it asks you what is the change, then it's 5.97 Celsius. If it asks you what is the freezing point of this solution, the solvent is water, and so it normally freezes at 0. This would be 5.97 degrees lower than 0, so the freezing point of my solution itself would be negative 5.97 Celsius. So watch out if they're asking you to calculate the change in the freezing point, or if they're asking you what is the freezing point. Okay, let's look at the next property, that is a colligative property. So the next property is boiling point. So let's think about how boiling point is affected. First of all, boiling point is the temperature at which the vapor pressure of the liquid equals the atmospheric pressure, or in other words, when the liquid and the gaseous particles are in dynamic equilibrium. And the boiling point will actually change, again, based on the number of particles of solute that you have in there. So it is considered a colligative property. So back to my particle diagrams. If I look at these two particle diagrams, there's my solvent, just pure solvent by itself, and there's my solution with the solute particles in the middle. So if I want to boil these, I have to heat up my particles, remember, so the vapor pressure is equal to the external pressure. So if I want to get these to boil, I have to raise their temperature so that they're moving fast enough, and when they boil, they are moving fast and they're turned into a gas, so they're spread apart and they hit each other, hit the walls of the container, they're moving pretty fast. So now consider that you want to turn these into gas, and you also want to turn these into gas. Which one's easier to turn into gas? It should be the solvent by itself, because when you have a solution, the solute particles are in the way, and so it's harder for these particles, the solvent particles, to spread out as much and to go fast enough to turn into a gas. And so it is harder to get a solution to boil compared to the pure solvent, and so I have to heat it up even more to a higher temperature, and so we call that the boiling point elevation. So basically a solution wants to stay as a liquid. It's harder to freeze it, so you got to freeze it at a lower temperature, and it's harder to boil it, so you got to boil it at a higher temperature. Mathematically, this one looks just like the other one. So instead of the F's, we're going to put B's. So delta TB, so B, is equal to KB times M times I. Same thing, except B for boiling as opposed to F for freezing. So this is the change in the boiling point. This is a constant that's different for each substance. This is your molality. And then this one is the number of ions that your ionic substance will split up into. So again, if it's covalent like this, we don't worry about it. If it's ionic, then we'll worry about it. And we'll see an example in a few minutes with it being ionic. So let's try this example here. It says, by how much will the boiling point be elevated if 100 grams of sucrose is added to 500 grams of water, and they give us Kb for water. So we're going to start with our equation. Delta Tb is equal to Kb times M times I. So delta Tb is equal to 0.52 Celsius per molal. That's my K. My M, I'm going to calculate separately on the side here. So it's moles of solute. My solute is sucrose, so 100 grams. Multiply that by 1 mole, 342 grams. So that's my moles of solute over kilograms of solvent. I have 0.500 kilograms. So my molality is 0.585 molal. I'm going to plug that back in here. So that's my K, then I have 0.585 molal. And my I don't worry about if it's covalent, which in this case it is covalent. So my delta TB is going to be equal to 0.30 Celsius. So what does that mean? That means that my boiling point elevates, by 0.30 Celsius. If they asked for what is the boiling point of the solution, you would look and see that water is your solvent. So normally pure water would have boiled at 100 Celsius. The solution has a 0.3 Celsius elevation, and so that means that my solution here boils at 100.3 Celsius. The third and final colligative property we're going to look at is vapor pressure. And so if you remember, vapor pressure is the pressure on the surface of a liquid caused by the vapor from that liquid. And so I'm going to go back to my particle diagrams here and talk about vapor pressure. So remember that in a liquid, some particles are moving fast, some are slow. The ones that are moving fast enough escape and become gas at the surface of that liquid. So comparing this versus this, the solvent versus the solution, if you think about it, in a solution, the solute particles are in the way, and so it is harder for these solvent particles in a solution to get to the surface and escape. And so less of your particles are escaping to become gases, and so you have less collisions and less vapor pressure. So the vapor pressure of a solution is lower than the vapor pressure of the solvent, again, because less particles are able to escape from the surface and become a gas. So we have vapor pressure depression. It goes down. And Raoult's law, there's a law that deals with this, that says the extent to which a non-volatile solute lowers the vapor pressure is proportional to its concentration. So again, that tells us that it is a colligative property. Mathematically, this one's a little bit different from the other ones. The equation for this one is delta P, the change in the vapor pressure, is equal to the mole fraction of the solute times P naught. Let's talk about what these are. So again, the delta P is the change in the vapor pressure, so how much it goes down by. X of the solute, that means the mole fraction of the solute, so moles of solute over the total moles. And then P naught is the initial vapor pressure. This is the pressure or the vapor pressure of the pure solvent. So I'm going to write that down. So if I did not have any solute particles in there, if it was just a pure solvent, this would be the vapor pressure of it. Let's try a problem. It says calculate the vapor pressure depression at 25 Celsius of a solution made by adding 43 grams of acetone to 120 milliliters of water. It tells us the vapor pressure of pure water at 25 Celsius is normally 23.8 millimeters of mercury. So I'm going to write my equation down. Delta P is equal to X solute times P naught. I'm looking for the delta P. My mole fraction, I'm going to calculate on the side. Actually, I'll just calculate my moles on the side at least. So I have 43 grams of acetone. Change that to moles. 58 grams per mole is the molar mass, and I get 0.74 moles. Then I have 120 grams of water. Change that to moles. 1 mole of water is 18 grams. You get 6.67 moles. So back to my equation here. So delta P is equal to the mole fraction of the solute. My solute is the acetone. So it's 0.74 moles of acetone over the total, so 0.74 plus 6.67. Sorry, my bracket's kind of weird. So this is my mole fraction that's in the bracket, and then times P naught, which is the vapor pressure of the pure solvent, and that is 23.8 millimeters of mercury. When you multiply that together, you end up with 2.4 millimeters of mercury. So again, what does that mean? That means that the vapor pressure of my solution is 2.4 millimeters of mercury lower than the vapor pressure of just the pure water. So if it asked you, what is the vapor pressure of this solution, you would say, well, this is the initial. This is how much it went down by. So you take this number minus this number, and that's going to give you the vapor pressure of the solution that you have. So as promised, we're going to talk about ionic solutes now and look at the I that we kind of ignored the last three problems. So remember that when ionic substances dissolve in water, what happens is that the ions kind of dissociate, and so let's say you have NaCl, for example. Let's write out the dissociation equation for NaCl. So you have NaCl solid, which is made up of Na plus and Cl minus as well. Those kind of separate physically, and so you get Na pluses and Cl minuses. So instead of one particle being in the way, now you have two particles being in the way. And you don't have that with covalent substances. Or for example, let's say you have AlF3. Well, for every particle of AlF3 that dissociates, you get an Al3 plus, and then you get 3F minuses. So really, for every one of these particles, you end up with 4 particles. And remember that colligative properties only have to do with the number of solute particles. It doesn't matter what they are. What matters is how many they are. And so to account for that, you put the I in your equations. And the I tells you how many ions your salt dissociates into. So for sodium chloride, the I would be 2 because I get 2 ions. For aluminum fluoride, the I would be 4 because I get 4 ions. So I have quadruple the effect. So let's try this one here. It says determine the freezing point of 350 grams of water to which 25 grams of CaCl2 has been added. Kf for water is given as 1.86 Celsius per mole. So it's talking about freezing point, so I'm going to put the equation here. Delta Tf is equal to Kf times m times I. And I'm going to solve for delta Tf. Kf is 1.86 Celsius per mole. My molality, I'm just going to do it here. I have 25 grams of the CaCl2. I'm going to convert that to moles. 1 mole is 111 grams, and then I'm going to divide by the kilograms, 0.350 kilograms. So this part by itself is just the M, and then the I, you look at CaCl2, and it should be 3. And the reason why it's 3 is because CaCl2, when it dissociates, you get a calcium ion, a 2 plus, and then 2 Cl minuses. Or if you want to draw a particle diagram, maybe that helps. You get a Ca2 plus, and then a Cl minus, another Cl minus. So when you dissociate that, those 3 physically separate, so you have 3 particles. So you multiply by 3 here. So punch that into your calculator, and the answer is delta Tf is equal to 3.63 is what I got. Now the question is asking you for the freezing point of the solution, not just how much it went down by. So it went down by 3.63 Celsius. The freezing point of water is normally 0 Celsius, and so if it goes down by 3.63, then the actual freezing point is negative 3.63 Celsius. The last thing I want to talk about briefly is, some practical applications to this stuff. So the freezing point depression, you see that when there's snow on the roads. What do they do to the roads? They add salt. And so what happens is the salt mixes with the ice, and it makes a solution, and so the freezing point lowers. The freezing point of salt water or salt ice is lower than the freezing point of just water. So let's say, let's say it's 20 Fahrenheit outside, and so that's way below the freezing point of water. Water will freeze at 32 Fahrenheit. So if they put enough salt on there, they can depress the freezing point so that it's not frozen at 20 Fahrenheit. It's frozen at a lower temperature. when it comes to ionic substances, you know, most of the salt that's on the road is actually calcium chloride. It's usually a mixture actually of calcium chloride and sodium chloride. Well, why would calcium chloride be better? Because you split up into 3 particles as opposed to 2 particles in NaCl. So your I for this one would be 3. Your I for this one is 2. So calcium chloride would be better at depressing the freezing point of water, so more ice would melt. The only thing with that, you have to take into account also the solubility and everything else. You've all had popsicles before. If you have popsicles and you try to like eat them, the first part that melts, it's usually like really sugary at first. That's because the solution that has the sugar and all the flavor and everything has a lower freezing point than your water. And so that melts first, and then at the end you'll just end up with like ice. An application for the boiling point for this one here, if you ever make pasta, a lot of people salt their water for 2 reasons. First, your pasta tastes better when you salt it, but then also it makes your pasta cook faster. The reason is because if you put salt in water, then that elevates the boiling point. So it might take a little bit longer to get it to boil, but once your water's boiling, maybe it boils at 105 Celsius instead of 100. And so now when you put your pasta, it's cooking at 105 instead of 100, and so it's a hotter temperature, so it's going to cook your pasta faster. So there's a lot of applications to these colligative properties all around us. All right, that's it for the lesson today. Hope you have a wonderful day. I'll see you guys tomorrow.